our subject, Automated Theory and Formal Language. The coverage of this subject are the following topics. First is the introduction of automated theory. Second, string and languages. Third, finite state machines. Fourth, context-free grammars. 5, push-down automata. And number 6 is the Turing machines. Okay, so let's proceed with our first topic, which is the introduction to automated theory. So what is automated theory? It is a branch of computer science that deals with designing abstract self-propelled computing devices that follow a predetermined sequence of operations automatically. That is according to tutorialspoint.com. And then, Wikipedia.org defined automated theory as the study of abstract machines and automata, as well as the computational problems that can be solved using them. It is a theory in theoretical computer science. In figure 1.0, it is the visualization of an automaton that recognizes strings containing an even number of zeros. The automaton starts in state S1 and transitions to the non-accepting state S2. Upon reading the symbol 0, reading another 0 causes the automaton to transition back to the accepting state S1. In both states, the symbol 1 is ignored by making a transition to the current state. Okay, so the major objective of automated theory is to develop methods by which computer scientists can describe and analyze the dynamic behavior of discrete systems, in which signals are sampled periodically. The behavior of these discrete systems is determined by the way that the system is constructed from storage and combinational elements. The characteristics of such machines include, first is the inputs, then outputs and states. So those are the 3 characteristics of such machine. So for the inputs, assumed to be sequences of symbols selected from a finite set 1 of input signals, namely set I is the set x sub 1, x sub 2, x sub 3, so on and so forth up to x sub k, where k is the number of inputs. While for output, sequences of symbols selected from a finite set z, namely set z is the set y sub 1, y sub 2, y sub 3, y sub 4, so on and so forth up to y sub k, where m is the y sub m, where m is the number of outputs. For the states, finite set q, whose definition depends on the type of automaton. The word automata is the plural of automaton, comes from the Greek word micron, which means self-making. An automaton is an abstract self-propelled computing device which follows predetermined sequence of operations automatically. An automaton with a finite number of states is called a finite automaton, or FA, or finite state machines, or FSM. Automatons are the abstract models of machines that perform computationals on an input by moving through a series of states or configurations. At each state of computation, a transition function determines the next configuration on the basis of a finite portion of the present configuration. As a result, once the computation reaches an accepting configuration, so it accepts that input And the most general and powerful automata is the Turing machine. And there are four major families of automaton. First is the finite state machine. Second is push-down automata. Third, linear bounded automata. And fourth is the Turing machine. The families of automata can be interpreted in a hierarchical form, where the finite state machine is the simplest automata and the Turing machine is the complex. It is the most complex. The focus of this project is on the finite state machine and the Turing machine. A Turing machine is a finite state machine, yet the inverse is not true. Okay, so the finite state machine, or the FSM, or what we call as FA, or finite automata. Okay, so the exciting history of how finite automata became a branch of computer science illustrates its wide range of applications. The first people to consider the concept of a finite state machine includes a team of biologists, psychologists, mathematicians, engineers, and some of the first computer scientists. They all shared a common interest to model the human thought process, whether it is the brain or in a computer. So Warren McCullough and Walter Pitts, two neurophysiologists, were the first to present a description of finite automata in 1943. Their paper entitled "A Logical Calculus Immanent in Nervous Activity" made a significant contribution to the study of neural network theory, the theory of computation, and cybernetics. Okay, so yan yung sinasabi ko na dalawang neurophysiologists. Si Warren at saka si Walter. Later, two computer scientists, J.H. Milley and E.F. Moore, generalized the theory to much more powerful machines in separate papers, published in 1955 to 1956. The finite state machines, the Milley machine, and the Moore machine are named recognition of their work. So kung ma-obserbahan ninyo, yung kanilang paper ay parang binase sa kanilang mga surnames. While the Milley machine determines its output through the current state and the input, the Moore machine's output is based upon the current state alone. An automaton with a finite number of states is called finite automaton or finite state machine. An automaton in which the state set Q contains only a finite number of elements called a finite state machines. So, FSMs are abstract machines consisting of a set of states na nire-represent natin gamit yung set Q, set of input events or tinatawag nating set I, a set of output events na pwede nating gamitin yung set Z, and a state transition function. The state transition function takes the current state and an input event and returns the new set of output events and the next state. Therefore, it can be seen as a function which maps an ordered sequence of input events into a corresponding sequence or set of output events. So this state transition function is from set I to set Z. Set I is the set of input while the set Z is the set of output events. Finite state machines are ideal computation models for a small amount of memory and do not maintain memory. This mathematical model of a machine can only reach a finite number of states and transitions between these states. Its main application is in mathematical problem analysis. Finite machines are also used for purposes aside from general computations, such as to recognize regular languages. So in order to fully understand conceptually a finite state machine, let's consider an analogy to an elevator. So I am expecting that all of you are fond of using an elevator. An elevator is a mechanism that does not remember all previous requests for service but the correct floor, the direction of motion, either it is up or down, and the collection of not yet satisfied requests for services. Therefore, at any given moment in time, class, an elevator inoperated would be defined by the following mathematical terms. So, hindi mawawala dyan yung states, inputs, and outputs. For the states, finite set of states to reflect the path history of the customer's request. For the inputs, finite set of input depending on the number of floors the elevator is able to access. We can use the set I, whose size is the number of floor in the building. And outputs, finite set of output depending on the need of the elevator to go up or down according to customers' needs. Okay, so an automaton can be represented by a 5-tuple Q, alphabet, transition function, initial state, and the final states. So, yan po yung 5-tuple that can represent a finite automaton or automaton. A finite state machine is formally defined as 5-tuple finite set of states, which is represented by capital letter Q, finite set of input symbols represented by capital letter I or uppercase letter I, finite set of output symbols represented by uppercase A, and the mapping of I times Q into Q called the state transition function, W mapping or W of I times Q onto Z called the output function, and A, uppercase A, which is a set of accept states where F is a subset of Q. So in this subject, you should be familiar on the sets, on the different kinds of sets. Either it is an empty set, an equal set, an equivalent set. So, dapat familiar po tayo sa sets. Okay. From the mathematical interpretation of the previous slide, so dito po, it can be said that a finite state machine contains a finite number of states. Each state accepts a finite number of inputs, and each state has a rules that describe the action of the machine for every input represented in the state transition mapping function. At the same time, an input may cause the machine to change states. For every input symbol, there is exactly one transition out of each state. In addition, any 5-tuple set that is accepted by non-deterministic finite automata is also accepted by deterministic finite automata. Okay. When considering finite state machines, it is important to keep in mind that the mechanical process inside the automata that leads to the calculation of outputs and change of state is not emphasized or delved into detail. So it is instead considered a black box. So look at the illustration here. the black box. So as you can see, there's an input symbol, the defining function, either it is an old state or a new state, and the output symbol. So this black box is just a depiction of the finite automata. Okay. So as a review, alphabet is a definite set of symbols. So, ito po ay napag-aralan na natin doon sa mga subjects natin when we are in second year. So, sa discrete structures, design and analysis of algorithms. So, hindi po mawawala itong topic na to. Okay? So, for the alphabet, which is a definite set of symbols, let's say for example, an alphabet consisting of symbols A, B, C, and D, where A, B, C, and D are symbols. For this string, a string is a finite sequence of symbols taken from alphabet. So, this symbol, the summation symbol, represent an alphabet. Okay? For example, CAB is a valid string on the alphabet set, which consists of the following symbols A, B, C, and D. For a length of a string, it is the number of symbols present in a string denoted by this symbol. Ito po. Ayan. So, for example, if uppercase S or the alphabet S is equal to the symbol CAB, so the length of a string is 6. Just count the number of symbols or the number of characters. So, if the length of the string is equal to 0, it is called an empty string. So, it is denoted by this symbol. Next, the clean star. The clean star, so represented by this symbol, is a unary operator on a set of symbols or strings that gives the infinite set of all possible strings of all possible length over alphabet, including the empty string. So, this symbol refers to or represent an empty string. So, the clean star equals to the union of the alphabet 0, 1, 2, so on and so forth, is the set of all possible strings of length P. So, for example, if an alphabet consists of symbols A and B, then the clean star of that alphabet is equals to an empty string A, B, A, B, B, A, B, 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 so on and so forth, as long as the symbols belongs to the alphabet consisting of symbols A and B. So for the clean closure or clean plus, the set clean closure or clean plus is the infinite set of all possible strings of all possible length over alphabet excluding empty string. So ang wala naman po dito, parang ganun din siya sa clean star, pero i-exclude po natin o hindi po kasama tong empty string. So, this is the representation of clean closure or clean plus. The clean closure symbol equals to the union of sets alphabet 1, alphabet 2, alphabet 3, so on and so forth. The clean closure or clean plus is equals to the clean star minus the empty string. So, sabi ko nga, parang din siyang ganun sa operation ng clean star, basta hindi lang po natin isasama yung empty string. Okay, a language. It is a subset of clean star for some alphabet. It can be finite or infinite. Let's say, for example, if the language takes all possible strings of length 2 over alphabet consisting of symbols A and B, then the language is equivalent to the symbols AB, AA, BA, and BB.